Hi everyone, this is the second lecture for linear algebra. In the last lecture, we introduced the determinant and the calculation techniques for calculating the determinant. And in this lecture, we're going to introduce the matrix, which we have encountered the concept of matrix. But first of all, let us define the number field. So a number field is denoted by F. It is defined to be as an arbitrary collection of numbers within which the addition, subtraction, multiplication, and the division by a non-zero number can always be carried out. And in our discussion, without any specific mention, we shall always assume that F is a number field. So let us define the matrix. Recall that in our first lecture, most of the calculation for determinant is based on an n by n, say array or matrix, but most matrices are not square. They are instead rectangular, and square matrix is only a special type of the matrix, so we shall define the general type. So a rectangular array of numbers of the field F in the form A11 to ANN to AN1. Sorry, so this is A1N to ANN. So this is called a matrix. So it is only a representation. And when our most of us say that a matrix of m by n, and when n equals to m, it is a square matrix. And now suppose that there are m variables, namely y1, y2 up to ym, and they have linear, homogeneous expressions in terms of n variables, namely x1, x2 up to xn, and it is denoted by y1 equals to, so let us use a11 x1 plus a12 x2 plus all the way down to a1n xn, and y2 equals to a21 x1 plus a22 x2 plus all the way down to a2n xn, and we have ym equals to an1 x1 plus an2 x2 plus all the way down to ann xn. And more concisely, we can denote it by yi equals to the summation for k equals to 1 up to n of aik xk for our I equals 1, 2 up to n. Oh, sorry. So this is I'm, not n. So it's I'm1, I'm2, and I'm n. And the transformation of the variables x1 up to xn into the variables y1 to ym. So that is from the row into the column. It's called a linear transformation. And the coefficients of the transformation form a matrix. Namely, so this should be M1 and Mn. So the linear transformation determines the matrix uniquely and vice versa. And if we denote A as an M by N matrix, then the scalar entry in the ith row and jth column of A is denoted by Aij, and it is called the ijth entry of A. And the diagonal entries in an n by n matrix is diagonal entries is Aij, such that A11, A22 up to ANN. So this is the diagonal entry, and they form the main diagonal of A. The diagonal matrix is a square matrix n by n, whose non-diagonal entries are 0. So diagonal matrix is in the form A11, A22 up to ANN, with all the remaining elements being 0, and is an n by n matrix. So an example is the n by n identity matrix, that is, the main diagonal is filled by the identity 1. And an n by n matrix whose entries are all 0 is called a zero matrix and is denoted by 0. And we say that two matrices A and B are equal if they have the same size. And that is, the number of rows and the number of columns are the same, respectively. And if their corresponding diagonal, column are equal. So that means the corresponding entries coincide. And recall that for yi equals to summation k from 1 to n of aik xk, for our I ranges from 1 up to I'm, and z I is defined to be the summation under k from 1 to n of aik xk, for our I still range from 1 up to I'm. And we have that yi plus zi equals to summation k from 1 to n of aik. So sorry, this coefficient means bik. So aik plus bik, and together their summation times xk. So this leads natural to the definition of the addition of matrices. So this means addition. So the sum of two rectangular matrices, namely A equals to aik and B equals to bik, of dimension n by n. Their summation is the matrix, namely C denoted by Cik, of the same dimension. And whose elements, Cik, are the sums of the corresponding, that is aik and bik. So we have C equals to A plus B, while Cij equals to Aij plus Bij. Oh, sorry, Bik and Cik, Aik. And the operation of forming the sum of A and B is called addition. And know that the sum of A plus B is defined only when A and B share the same size. We shall offer a result without proof. So if we let A, B, and C be matrices of the same size, then we have, first of all, A plus B equals to B plus A, so that is symmetric. And secondly, we have A plus B, then plus C equals A plus the sum of B and C, so that is associative. And thirdly, we have that A plus the 0 equals to A, and this is the addition identity. And fourthly, so if we are given A, there exists minus A with the same size of A, such that A plus minus A equals to 0. So that is the inverse, the addition inverse. So this is the property for matrix addition. And that is why we call this linear algebra instead of matrix theory. But in fact, there is some courses named by matrix theory, which contain more advanced stuff in linear algebra, especially the concern falls into the matrix operation or linear transformations itself. And note that the introduction of the addition is smooth, but in the last result. The introduction, however, is not that smooth, since minus a equals to minus 1 times a. So in fact, based on what we have so far, we can now derive the fourth result directly. We need also the so-called scalar multiplication of matrices. So let us define it. So we let A denote the matrix where I ranges from 1 up to m, and J ranges from ik, and k ranges from 1 to n. And we let alpha be a number or a scalar in F. And if we have C equals to Cik, and its elements are such that, or we say that C equals to alpha A, it really means that Cik equals to alpha times Aik. And the operation of forming the product of a matrix by a scalar is called the multiplication of the matrix by a scalar. So in matrix, we can say that A times alpha times A11 up to A1n. This is AM1 to AMN. So it actually equals to alpha times A11 up to alpha times A1n, and alpha times AM1 to alpha times AMN. So now it makes sense to derive the fourth result in the last theorem, and we shall offer more theorems for the scalar multiplication of matrices. So we let alpha and beta lives in F, being scalars, and A, B are matrices. More specifically, we want it to be as general as possible, so we say they are rectangular matrices of the same size. Then, firstly, we have alpha of A plus B. So actually, we can say, since we are also considering the addition, so we shall continue our counting in the last theorem. So this is the fifth. The fifth result. So alpha times the summation of A and B equals to alpha times A plus alpha times B. And next we have that alpha plus beta, the sum times A equals to alpha times A plus beta times A. And then we have that alpha times beta and then times A equals to alpha times beta times A. Therefore, the difference A minus B of two rectangular matrices of equal size is defined to be A minus B equals to A plus minus 1 times B, and our result in the last theorem could be proved. And note that alpha A, the determinant, or I use determinant of alpha A, equals to alpha to the nth power times the determinant of A. Where A is a square matrix of order n and alpha is a scalar. Now one may find that the introduction of determinants are with respect to square matrices. And this is done for a reason, since determinants are not typically used for rectangular matrices. Otherwise, we can see that there are situations where modified version for the determinant is required. And we shall encounter this modified treatment for rectangular matrices in more specific contexts. However, the standard determinant concept remains a fundamental concept for most concern of our calculation, since we have well-defined calculations and properties. So now we have the addition of matrices and the scalar multiplication of matrices. It left us to consider the multiplication between matrices. So suppose that we have variables z1 up to zm are expressed by y1 up to yn by the transformation di equals to k from 1 to n of aik yk for I equals 1 to up to n, so up to n. And we further have y1 up to yn are expressed by x1 up to xq by the transformation yk equals to summation k j from 1 to q of bkj xj, where k ranges from 1 up to n. So if we substitute these expressions for yk, and we shall express each z1 up to zm in terms of x1 up to xq by means of the composite transformation, namely, we have substitution, tuition yields zi equals to summation k from 1 to n of aik times the summation j from 1 to q of bkjxj, and it equals to j from 1 to q of summation k from 1 to n aik bkj then times xj, where I ranges from 1 up to n. And in accordance with this, we can formulate the definition of products between two matrices. So the product of two rectangular matrices, namely, if we shall denote A by A11, A12 up to A1n, A21, A22 up to A2n, all the way down to AM1, AM2 up to AMN, while B expressed by B11, B12 up to B1Q, B21, B22 up to B2Q, all the way down to BN1, B2, BN2 up to BNQ. And we shall say that their product is C equals to C11, C12 up to C1Q, C21, C22 up to C2Q, all the way down to CM1, CM2 up to CMQ. in which that the elements Cij is the product of the ith row of A and the jth column of B. So that is where our Cij equals to the summation k from 1 up to n of A, I, k, B, k, j, where I ranges from 1, 2, up to m, and j ranges from 1, 2, up to q. And the operation of forming the product of the given matrices is called the matrix multiplication. So obviously, the definition of A times B shows that, so for example, we have A is of m by n, and B is of n by q. And then their product is of m by q. So we see that the number of rows of A and the number of columns of B has to coincide. In particular, multiplication is always possible when both factors are square matrices. Of course, they have to be of the same size. And moreover, suppose that A is m by q and B is n by q, then we see that the operation could not be done, and one can check by the definition why this is not the case. And furthermore, if we shall use the row I of A to denote the ith row of A, then we have that row I of A times B equals to row I of A times B. And now we shall introduce a theorem containing the properties of matrix multiplication, and recall that in saying IM, we really mean that it is the m by m identity matrix. So that means IM times x equals x for all x that lives in I to the m. So now let us state and prove the theorem 3. So let A be an m by n matrix, and let B and C have same size, or have size for which the indicated sums and products are well defined. Then we have, firstly, A times B times C equals to A times B and then times C. So that is associative. And know that in the matrix addition, the first result is the symmetric property. But this is not the case for multiplication. That is, A times B is not necessary to be equal to B times A. The second result is that A times B plus C equals to A times B plus A times C. So this is called the left distributive law. And in contrast, we have the right distributive law. So that is A plus B and then times C equals A times C plus B times C. So this is called right distributive law. And also, for scalars, we have alpha times A times B equals alpha times A and then times B, and also equals A times alpha times B. and this shall be true for all alpha scalars. And the fifth result is the multiplication identity. So that is IM times A equals to A, and it equals to A times IN. Recall that A is I by N. So that is the multiplication identity. So, bunch of remarks. The first I just mentioned is that B times A does not necessarily coincide with the result of A times B. And also, the cancellation law does not hold. So that is A times B equals to A times C does not imply that B equals to C in general. And also, so if A times B is 0, this does not imply that A equals to 0 or B equals to 0. And let us see an example why matrix operation is so powerful in solving linear systems. Or this is the motivating example. So suppose we're considering x1 equals to y1 minus y2, and x2 equals to y1 plus y2. And we have another y1 equals to z1 plus z2 plus z3, and 2z3, sorry. Let me write it in a more clear way. And y2 equals to z1 minus 2z2 plus z3. And we have, lastly, z1 equals to u1 plus u2, and z2 equals to u1, while z3 equals to minus u1 plus u2. And if we want an expression for u1 and u2 with x1 and x2, we shall need to multiply the corresponding matrices. So that is, if we write for the first matrix, 1, minus 1, and 1, 1, representing y1 and y2 respectively. And if we multiply by the second matrix, which is the coefficients of each z1, z2, and z3, so that is 1, 1, and 2, and in the second row is 1, minus 2, and 1. And then we have the coefficients for u1 and u2, so that is 1, 1, 1, 0, and minus 1 and 1. So multiplying these three matrices together, so even though we have the associativity, we still, for example, just to calculate the first multiplication, then calculate the multiplication of the remaining. So we have 1 minus 1 multiplying 1, 1 yield the first entry, so that is 1 times 1 plus minus 1 times 1, so that yields a 0. And then let us start with another direction, so that is 1 minus 1 times 1 and minus 2. So that is 1 times 1 plus minus 1 times minus 2, so that is 3. And similarly, when 1 minus 1 times 2 and 1, this gives us a 1. Same thing happened for the second row with each column in the second matrix, and that gives us 2, minus 1, and 3. And now the first entry comes from the first row times the first column. So that is 0 times 1 plus 3 times 1 times 1 times minus 1. So that is 2. And we move to the second column, and this is as a 1. Same thing happened for the second row and the first column, and that gives us a minus 2. And lastly, we have 5. So therefore, starting with the expression for x1 and ending up with the corresponding coefficients for u1 and u2, we shall have that x1 equals to 2u1 plus u2 and x2 equals to minus 2u2 plus 5, that is u1, plus 5u2. And we're done. So a very useful fact is that when a rectangular matrix A is multiplied, for example on the right, by a diagonal matrix with elements on the main diagonal, being A11, A22, and ANN, then the columns of A are multiplied by the diagonals respectively. And now we have addition, subtraction, multiplication, and also the underlying inverse of the multiplication, which is the division, which we have not introduced yet. The inversion of the multiplication, that is the division, however, relies on the invertibility of the matrix, so we do not introduce here. Instead, we shall introduce it in the invertible matrix theorem. Instead, we shall recall another very useful concept. It's called the power of matrix. So if A is n by n, and if k is a positive integer, then we also want 0 to be included. So this is defined to be the positive side of integer union 0. Then ak denotes a times all the way down to a, and there are k times. So if a is non-zero and if x is in F, so namely Fn, so that means x is an n-dimensional vector in the underlying number field, or vector field generated by the number field. So we have a to the k times x is the result of left multiplying x by k times. So that is a times all the way down to a, there are k times, and then times x. And also, since we have the associativity of the multiplication of matrices, we can always interchange the relationship. And also for the scalar multiplication, as we see in the last theorem. And moreover, if k shall be 0, we have a to the 0 equals to I n. So that is a naught times x equals x itself. So a naught is the identity matrix. And now we shall introduce the property for the power of matrices. So still, let A be an n by n matrix, and for k1, k2 be two non-negative integers. Then we have, firstly, a to the k1 and then times a to the k2 equals to a to the k1 plus k2. And secondly, we have a to the k1 and then to the k2 equals to a to the k1 times k2. So yes, most of the results in the basic algebra course are followed by the matrix. Only for somewhere we have the modifications. And recall that in studying the determinant, we also introduced before the invertible of the inverse, we have the concept of the transpose. So let us generalize the transpose of the matrix. So given an n by n matrix A, the transpose AT, denoted by AT, is the n by m matrix, and the formation of the transpose of A follows from the one we talked about in the determinant. So that is the rows becomes two columns, while the columns becomes the rows. So actually, let me, so so let us use theta. Wow, so let us just use the A11, A12, A21, and A22. So the transpose goes like A11, A12, and A21, A22. And now we shall talk about the properties of the transpose. So let A and B be matrices with sizes that are appropriate for sums and multiplications. Then we have, firstly, A transpose and then transpose equals to A. And secondly, A plus B, the sum transpose equals to the transpose of the sum of each transpose. So the transpose of the sum equals to the sum of the transpose. And thirdly, for the scalars, we have alpha A together transpose equals to alpha times A transpose. But for the multiplication, we have the order reversed. And now we shall introduce a concept called the polynomial of matrix, which turns to be very useful. So in saying a polynomial, we really mean the integral rational function. So consider a polynomial with coefficients in the field f given by, namely f of t equals to alpha naught t to the m plus alpha 1 t to the m minus 1 and plus all the way down to alpha m times t to the 0th power, which is 1. So that is alpha m. And then by f of a, where a is a matrix, we really mean that f of a equals to alpha naught a to the m plus alpha 1 times a to the m minus 1 and plus all the way down to alpha m times the identity im. And we shall define in this way a polynomial of a matrix, in a matrix. And also, suppose that f of t is the product of g of t and h of t. And the polynomial f of t is obtained from g of t and h of t by multiplication term by term and collecting the similar terms. So in this way, we can make use of the multiplication rule for powers. So that is, we have t to the p times t to the q equals t to the p plus q. And since all the operations remain valid when the scalar t is replaced by the matrix A, so we really have that f of A equals to g of A times h of A. In particular, we have g of A, h of A equals to h of A, g of A. So that is, the two polynomials in one and the same matrix are always permutable. And recall that when we have the determinant being 0, it means that our matrix is not invertible, and we also mean that our matrix is singular. So we have that a square matrix A is singular if its determinant vanishes. Otherwise, we say A is non-singular. And now let A equals to AIK be non-singular, be a non-singular matrix. And let us consider a linear transformation with coefficients of the matrix A. So that is yi equals to the summation k from 1 to n of aik times xk, where I ranges from 1 up to n. And when we regard this equation for x1 up to xn and observe that the determinant of the system is by our assumption different from 0 since it is non-singular, so we can express x1 x2 up to xn in terms of y1 up to yn since it is invertible. So we have that the inverse, namely xi, equals 1 over the determinant of A, so that is denoted by this way, times our A11 up to A1 I minus 1, Y1 and A1 I plus 1, and up to A1n, A21, A2 I minus 1, and Y2, A2 I plus 1, and all the way down to A2n, and an1, an I minus 1, yn, an I plus 1, and all the way down to ann. And this equals to the summation of k from 1 to n of aik to the inverse times yk, where I ranges from 1 up to n. So we have obtained the inverse transformation of this equation. So the coefficient matrix of this transformation, namely a minus 1 equals to aik e to the inverse, will be called the inverse matrix of A. And recall we introduced the terminology invertible for determinant or n by n array. And let us generalize this to n by n matrix. So an n by n matrix A is invertible if there exists an n by n matrix C such that CA equals to IN equals to AC. And in this case, C is the inverse, or it is called the inverse of A. So in fact, in this definition, C is uniquely determined by A, since if B is another matrix, so if B is another matrix such that BA equals to IN equals to AB, then we have B equals to B times IN equals to B times, so for example, AC. And it equals to B times A, then times C. And we know B times A is IN, so that is IN times C equals to C. So we know that a matrix once has an inverse, then it is unique. And the unique inverse is denoted by A to the inverse. So let us now prove a theorem. If A is n by n invertible matrix, then for all B being an n-dimensional vector, the equation AX equals to B has a unique solution. Namely, X equals to A inverse B. Sorry. So let us prove it. So the proof is divided into two parts. The first part, we shall prove that the existence of the solution, and then we shall prove the solution is unique. So let us choose B lives in Fn arbitrarily. So step 1, the existence. So the existence is trivial since A inverse B is substituted by 4x. So we have that AX equals to A times A inverse of B. So we have IN of B, IN times B, which is B. So A inverse B is a solution. And then we shall prove the uniqueness. And it suffices to show that if U is another solution, and we want to have that AU equals to B. So since AU equals to B and A is invertible, we have that A inverse times AU equals to A inverse times, since AU equals to B, so that is A inverse times B. So that really means IN of U equals to A inverse of B. So that is U equals to A inverse of B. Therefore, the uniqueness follows. And as we did in the last lecture, a natural question to ask is that when is a matrix invertible? Since obviously not all matrices are invertible. And in introducing that concept and introducing an effective algorithm in calculating the inverse of a given square matrix, we need the concept called the adjoint. So still, let A equals to Aij be an n by n matrix. Then The adjoint of A denoted by A star is defined by A11, A21 up to AN1, and A12, A22 up to AN2, all the way down to A1N, A2N up to ANN. And we see this looks very much like the transpose, since our usual way of introducing the row is now the column. And we have now encountered the really concept of what A11, A21, and AN1 means. However, we have introduced this concept in the first lecture. Still, let us do an exercise. So that is, given A equals to 1, 1, 1, and 2, 1, 3, followed by 1, 1, 4. And we want to find A star, the adjoint of A. So let us start with A11. So A11 is in fact minus 1, since it is at 1, 1 entry. So it times 1 plus 1. And then we remove the first row and first column, and the remaining is 1, 3, 1, 4. So 8 times the determinants of 1, 3, and 1, 4. And this gives us 1. Similarly, we have A1, 2 equals to minus 1 to the 1 plus 2. And times we remove the first row and the second column. Then we have 2, 3, 1, 4, which is minus 5. Similarly, we can calculate A13 equals to minus 1 to the 1 plus 3. In times, we removing the first row and the third column, and the remaining is 2, 1, and 1, 1. And this gives us a 1. Also, we have A21 equals to minus 1 to the 2 plus 1. And it times 1, 1, and 1, 4. This gives us a minus 3. Then for A22 equals to minus 1 to the 2 plus 2 times 1, 1, and 1, 4, which gives us a 3. For A23 equals to minus 1 to the 2 plus 3 and times the determinant of 1, 1, 1, 1, which is 0. And for A31, we have, so minus 1 is just to the fourth power, so it's just 1. So it is in fact 1, 1, and 1, 3. And this is 2. Well, A32 equals to, and this time it's minus 1, so minus 1 times 1, 1, and 2, 3. So that is minus 1. And similarly for A33, it equals to minus 1 to 3 plus 3, so that is 1. So it is just the determinant of 1, 1, and 2, 1, which gives us a minus 1. So A star equals to, recall our definition, it starts with the row, the A11, A12, and A13. Instead of being the row, it becomes the first column. So we have the first column being 1, minus 5, and 1. Similarly, the second row becomes the second column, and that is minus 3, 3, and 0. And the remaining is 2, minus 1, and minus 1. And now let us state some results without proof. The first result is that if A is an n by n matrix, and A star is its adjoint, then we have A times A star equals to the determinant of A times In. So that is still equal to A star times A. So this introduces a kind of the underlying meaning for the adjoint. So that is, it is a mapping to the identity matrix of the corresponding matrix. And a corollary follows. So still, A is n by n and it is non-singular. Then we have A star, the determinant of the adjoint equals the determinant of A to the n minus 1th power. And know that this holds when A is singular. So if A is n by n, then we also have A star, the determinant equals to the determinant of A to the n minus 1th power. And now after introducing the adjoint and its properties, we can now derive a criterion for being invertible. So we say that an n by n matrix A is invertible if and only if its determinant does not vanish. And moreover, if this is the case, we can find its inverse. So if A is invertible, then we have A to the inverse equals to 1 over the determinant of A times A, the adjoint of A. And now we shall introduce some properties of the invertible matrix. Invertible matrix theorem. So firstly, if A is invertible, then A inverse is also invertible. Moreover, we have A to the inverse, then to the inverse coincides with A. And secondly, if A and B are n by n invertible matrices, then so is their product A times B. And the inverse of A times B is the product of the inverses of A and B in the reverse order. So this taking inverse of the product of matrices is order reversing. So that really means A times B all to the inverse equals B to the inverse times A to the inverse. And now let us consider the composition between the transpose and the invertible and the inverse. So still, if A is invertible, so is its transpose. Moreover, the inverse of the transpose equals to the transpose of the inverse. So that is, we have A transpose then to the inverse equals to A to the inverse and then transpose it. The next result is a relationship between the determinant of the original matrix and the invertible and its inverse. So still, if A is invertible, then we have A, its inverse, determinant of its inverse equals to the determinant of itself to the inverse. And the last result is that if A is invertible, then its adjoint is also invertible. And also we have that A star is inverse. It's just This guy, one can recall the way of finding the inverse once the matrix is invertible. And then we now shall introduce the famous invertible matrix theorem. So sorry for that. This is not the invertible matrix theorem. This is only the properties for invertibility. Okay, so this is the invertible matrix theorem. So if we let A be an n by n square matrix, then the followings are equivalent. First, A is invertible. Second, A has n pivots, pivot positions. So that really means consider a matrix. If we reduce it to the reduced echelon form, for example, we have A12, A23, and all the remainings are 0, then we have that there are only 3 terms that are not free variables. So we have there are 3 pivots. So loosely speaking, the pivot positions, the number of pivot positions is those variables that appearing at the leftmost when it is under the reduced echelon form, and we shall introduce this concept later, where we shall introduce the Gauss elimination. And it is also equivalent to that Ax equals to 0 has only trivial solution. Then we also have that the column of A form a linearly independent set. So we use column of A this way, forms a linearly independent set. E, we have the linear transformation. Namely, X maps to Ax being 1 to 1. So that is, it is injective. And by saying onto, we mean it is a surjective. And by saying it is a 1 to 1 and onto, we mean it is a bijective. And next is that the equation Ax equals to B has at least one solution for all B lives in F. The next result is that the column of A spans Rn. Sorry, should be Fn since our underlying number field is F. But in most cases, we are considering real number systems, so a substitution of R is also valid. We also have that linear transformation. That is, X maps to Ax from Rn to Rn is surjective. That is, it is an onto. So we have it is 1 to 1 and we have it is surjective. So it is in fact bijective. And also we have A transpose is also invertible. If and only if there is C and D matrices, n by n matrices such that CA equals to IN and AD equals to IN. And know that C and D needs not to be coincide. And this is all for today's lecture. In the next lecture, we shall introduce the partitioned matrix. And if we have enough time, we will talk about the elementary matrices. And also, we may talk about some results from the vector space and subspace. So perhaps elementary matrix. Okay, so that's all for today's lecture. Thank you for watching and see you in the next lecture.